Hello physics students, this is Dr. Brenzy. We're beginning a new unit today, and this unit is going to be about circular motion. And so today's lesson is going to be about teaching you some of the basic circular motion and to talk about how circular motion works in a very basic level. You may have already dealt with circular motion, at least in middle school science, when you talked about planets and the solar system. And you may have come across these two words, revolution versus rotation. So there's a distinct difference between the two, even though sometimes in everyday life we kind of combine the two, and maybe even we use rotation when we should actually be using revolution. So what is the difference between these two? A revolution is like the Earth's motion around the sun. So it's when an object actually completes a full circle around a point outside of its own body. Compare that with rotation, like a spinning top, where you have something spinning around a point that's located in the body of the object itself. In other words, this top is spinning around this point right here. So to put that more formally, a revolution is the completion of a full circle around a point outside the body, and a rotation is the completion of a full circle spin around a point inside the body. So here are a couple of other words that might not be as familiar with you when we're talking about circular motion. I want you to take a quick look at these two, and I want you to see if you can come up with the difference between what period is and what frequency is. When you've come up with that definition or that difference, unpause the video and we'll continue together. Okay, so I'm going to assume that you've paused the video. So a period is the amount of time that it takes to complete just one lap around a circle. Compare that with frequency, where we have a set amount of time and we're trying to count the number of revolutions or rotations we make in whatever time this is right here. So, to put it more formally, period, tau, we represent that as a Greek letter tau, and let me write that here. T-A-U is how we pronounce it. Tau is the amount of time it takes to complete one revolution. Now this is an AP topic only, but if you want to put it in your notes, advanced students, you can certainly go ahead, but I'm not going to hold you responsible for it. Frequency, which is represented by the Greek letter nu, N-U, is the number of revolutions that can be completed in a unit of time. One very common term that you already or might be familiar with is RPM, which means revolutions per minute. So if you look at the instrument panel on your car, you might see this, what's called a tachometer, and tachometer tracks how many revolutions per minute your car engine makes. Well, that is a measurement of frequency. How many revolutions can you complete in a certain amount of time? Now, in physics, we usually don't use revolutions per minute. Instead, we use revolutions per second. So be aware of that. It's just that in engineering, sometimes they like to use revolutions per minute. But in physics, we use revolutions per second. Okay. Now, even though this is going to pertain to something that's only for AP Physics, I think radians are something that's important enough that all of us should know. So I'm going to ask all of us to take notes on this. A radian, you probably learned in math class already, but it's a good refresher here. A radian is the angle subtended by an arc whose length is equal to the circle's radius. What do I mean by that? We can take a meter stick or some sort of measuring device like a tape measure and actually measure one complete radius. And when we do that along the circumference of the circle, we get an arc length. And the length of this arc, when it's completely equal, or when it's exactly equal to the length of the radius, then the angle that's subtended by that arc length is called 1 radian. So to give you an idea of how radians work, there are 2 pi radii. In other words, if I did this around a complete circle, how many of these arc lengths would I get? How many radiuses, or radii actually is the plural word? We would get 1, 2, 3, 4, 5, 6, and 6 would bring us a little bit less than where we need to be. It's actually somewhere around 6.28, but it's exactly equal to 2 pi. So there are 2 pi radii of arc length in the circumference of a circle. Well, that means that as far as angle is concerned, normally you use 360 degrees, but if we're to figure out the total number of radians in a circle, you would end up with 2 pi radians. So it's a little bit more than 6. You could also say, well, how many radians are in a half circle? Well, there are pi of those because it takes pi number of these arc lengths to equal half of a circle. So let's bring that to something that's important in physics, and that is linear speed versus angular speed. So when we have motion around a circle, oh, and by the way, oops, I didn't draw this here, but this angular speed, excuse me, this is going to be an AP only topic. So those of you in advanced physics, you don't need to know about angular speed, but you need to know about linear speed. So let's talk about linear speed. So when something is traveling around a circle, we can actually take the amount of length that it covers and divide it by a certain amount of time. So let's say that it covers 3 meters plus another 3 meters to give us a total of 6 meters, and it goes 6 meters around the circumference of the circle in 2 seconds. So we would say that the linear speed of this object going around the circle is 3 meters per second. So we'd have 6 meters, whoops, meant to do that in red. So we have 6 meters traveled in 2 seconds. That would be 3 meters per second. Okay. Now, let's compare that with angular speed. Angular speed is a measure of how many radians our angle changes as over time. What is the rate of angle change? Well, let's say that I cover 2 radians of angle in 2 seconds. So I could say that my angular speed is 2 radians divided by 2 seconds. Or we could say 1 radian per second. Okay. Now, a little bit about radians and unit conversions before I go on here. Radians are actually a dimensionless unit when it comes to unit conversions. Okay. And that will come up a little bit later in our AP Physics, why that's dimensionless and why that's important. But for now, just note that that's a dimensionless unit. Okay. So let's write a definition of linear speed. So linear speed is the rate at which a point changes its position along the circumference of a circle. and the units of linear speed are meters per second. So you can actually figure out the linear speed, v, if you know the radius of the circle and if you know the period that it takes to go one full revolution around. Well, 2 pi r, that is equal to the circumference of an entire circle, right? And it takes one period, tau, to go around that circle, so of course the linear speed is going to be our total distance divided by our total time. And that's how we come up with that formula, v equals 2 pi r over tau. Now the interesting thing about linear speed is that the farther you're out from the center, the greater your linear speed is. So if you were to double the radius of an object, you would actually have to double its linear velocity. So linear speed gets larger with a larger radius. Okay, this is an AP topic, so advanced physics students, if you don't want to listen to this, you can fast forward ahead to the next video. Or not next video, excuse me, next slide. So angular speed, in physics, we designate that by the Greek letter omega. Angular speed is the rate at which a point changes its angular position. Its units are radians per second, and I showed you a little demonstration of that. So the formula for calculating angular speed is, well, we're going to cover 2 pi radians in a full circle, 2 pi radians of angle, and divide that by the total period that it takes to cover that full circle. And that will give you your angular speed. Now there's a relationship between linear speed and angular speed. And that relationship is omega times r equals v. Now here's why I told you why radians are dimensionless units. So I told you that omega is in terms of radians per second. And then if we multiply that times a distance in meters, we should get meters per second, right? But we have this thing radians still attached. And that's why I told you that radians are actually a dimensionless unit when it comes to unit conversions. So we don't even, when we're doing unit conversions, we don't even think of radians as a unit. It immediately goes to meters per second. All right. Now, unlike linear speed, angular speed does not depend on radius. So even though these two dots are going at a different linear speed, they cover the same amount of arc in the same amount of time. Therefore, the angular speed does not depend on radius. Those two dots cover the same angular, the same amount of angle, so they have the same angular speed. Okay, now that I've defined some important terms for you, let's talk about what uniform circular motion is, because that is what I entitled this lesson, is uniform circular motion. So an object is in uniform circular motion if its angular or linear speed remains constant over time. So advanced students, we didn't talk about angular speed with you, but you can actually use linear speed. So if we have a point around a circle, that's a bad looking circle. If we have an object traveling around a circle, we would want this object to go at a constant rate. We don't want it to speed up or slow down. We just want it to go at a constant speed around the circle. If it goes at that constant speed, then we can say that the circular motion is uniform. But if we have things speeding up and slowing down and speeding up and slowing down and speeding up and slowing down, that is not an example of uniform circular motion. Okay, one last term that I need to talk to you about is called centripetal acceleration. And we get the word centripetal from two Greek words. Centri is what we call center, and this word pedal, or this stem pedal, which is a word, comes from the Greek word, meaning seeking. So a centripetal acceleration is a center-seeking acceleration. And why do we say it's a center-seeking acceleration? Well, what happens when this dot travels around this circle? At a time t, any given time t, it will be traveling tangentially to the circle. So it's going to go at a tangent to the circle. But a moment later, it is actually going at a slightly different direction. Now, the change in the velocity vector is a vector that actually points in toward the center of the circle. And we know that acceleration is equal to delta v divided by delta t. So if delta v is pointing inside of the circle, then our acceleration also has to point toward the center of the circle. And no matter where I am along this circle, the acceleration is going to be in toward the center of the circle. And that's why we call this centripetal acceleration, center-seeking acceleration, because its direction is always going to be pointed toward the center of the circle. Centripetal acceleration changes the direction of an object's velocity, but not its magnitude. So if I were to measure the speed of something in uniform circular motion, its speed would remain the same. But since the velocity is constantly changing direction, I can't say that the velocity remains constant. And I can't say the acceleration remains constant, but I can say that the magnitude of the acceleration remains constant. So the formula we have for calculating centripetal acceleration, acceleration toward the center of the circle, is a sub c, centripetal acceleration, equals v squared. This is a v, AP students, not that Greek letter nu. This is the letter v. V squared divided by r. Now, for those of you in AP, you can also write down this formula that centripetal acceleration is equal to the angular velocity squared times r. And this centripetal acceleration always points toward the center of the circle. So let me wrap up this video with a quick example, or an example, of calculating some of these basic facts that I gave to you today. And by the way, I'm going to reserve this one. That's just an AP problem since I only talked about angular speed for AP. So we have a Ferris wheel with a radius of 14 meters turning counterclockwise. Counterclockwise means opposite of a clock. So if we start here, we're going to go in the opposite direction of an old-fashioned clock. So this Ferris wheel is turning counterclockwise about a horizontal axis through the center. So there's an axis that is going through the center of the circle, and our Ferris wheel is rotating around that axis. The linear speed of the passenger on the rim, so we have a little passenger down here, is constant and equal to 7.00 meters per second. So if we were to measure this person's instantaneous velocity, it would be 7 meters per second, going tangentially away from the circle, or going tangential to the circle, excuse me. So I have to calculate the time it takes for one revolution, I have to calculate the angular speed of the wheel, and I have to calculate her centripetal acceleration at the top. So let's redraw the Ferris wheel. This is what I might do on my paper. I would say it has this person has a linear speed of 7 meters per second. And this person is at a radius of 14 meters from the center of the circle. And in part A, I have to calculate the period tau. That's the amount of time for one revolution. In part B, I have to calculate omega for those of you in AP. And in part C, we have to calculate the centripetal acceleration. All right, so part A. I'm not given any sort of time, but I am given a linear velocity, and I know that linear velocity is equal to 2 pi r divided by tau. I don't know tau, but I do know that the velocity is 7 meters per second, so I can fill in 7 meters per second there, equals 2 pi times 14 divided by tau. And if I were to multiply both sides by tau, I would get 7 tau equals 2 pi times 14. And then I could divide both sides by 7. That would divide the 7s out, and I'm left with tau equals 2 pi times 14 over 7. But I know that 14 over 7 is the same as 2 over 1. So I have 4 pi. It's 4 pi. So 4 times pi is about 3.5 seconds. Okay. So that's the amount of time it takes to go one revolution. Part B. Part B is very quick. Omega is equal to V divided by R. So we just need to take 7 divided by 14, and we find that this is going at a angular velocity of 0.5 radians per second.
We're back. It seems like that was not done.
Okay, sorry about the interruption there. I had to actually pause the video to teach a class. So for our angular velocity for this particular problem, the Ferris wheel, we have 0.5 radians per second. And let's finally finish this off by doing part C and figuring out what the centripetal acceleration is. And that's going to equal v squared divided by r. So if we take 7 and square that number, and then divide that by the radius r, we have 49 divided by 14, and that turns out to be 3.5. And that's going to be meters per second squared. Let me... 3.5 meters per second squared. Okay, there you go. Okay, so that's an example of calculating period and angular velocity and centripetal acceleration. All right, hope you found this educational, and look forward to teaching you more about circular motion in class soon. Bye.